Welcome back to the Deep Dive, where we crack open the most complex technical blueprints in enterprise architecture and, well, distill them into knowledge you can use right now.
Today, we are focusing on something that is, I think, the very foundation of corporate access and identity. We're talking about Active Directory.
The master key.
Exactly. It's the master key to your entire enterprise. And the moment you decide to move even a small piece of that infrastructure into the cloud, the security stakes they shoot through the roof.
They truly are astronomical. I mean, we're not talking about deploying a standard web server here, are we? We're talking about the absolute central nervous system of identity and access management for most companies. And if you get this one specific architectural task wrong, I mean, if you accidentally route your domain controllers, your DCs to the public internet, even for a moment, you are inviting an operational disaster, that is. It's just difficult, if not impossible, to recover from swiftly.
It really is.
It's probably the single biggest cloud migration risk for any established enterprise.
It is absolutely the most common failure point we see. You know, architects often treat a domain controller like it's just any other virtual machine they're deploying in AWS.
Just another EC2 instance.
Right. And they forget that its entire communication structure as well. It's ancient, it's fragile, and it is absolutely essential. We just can't rely on default settings. We need to build a fortress.
So our mission today is to give you that complete end-to-end architectural blueprint. This is your definitive shortcut to deploying domain controllers securely, making sure they live deep within AWS private subnets, completely shielded from the public eye.
We're aiming for total invisibility, total resilience.
And we'll break down the truly complex layers that govern this. Things like how to handle VPC routing, why the NAT gateway isn't always enough, the crucial role of VPC endpoints, and the tricky world of security group rules.
And that replication killer. We have to talk about the RPC high ports.
Oh, absolutely. Okay, let's unpack this. Let's start with the absolute non-negotiable rule that governs everything we're about to build today. Invisibility.
The first principle, the one that must be, etched in stone for every single architect out there, is that domain controllers must never, ever be reachable from the public internet.
Never.
This isn't just a best practice. It's literally survival.
And when we say reachable, we're talking about blocking traffic to the protocols they use, right? We're protecting things like Kerberos on port 88 for primary authentication.
Main login protocol.
LDAP and LDAPS for directory queries on 389 and 636. SMB for those critical SYS-VUL and netlogon shares on 445.
Which is how group policy gets delivered.
Right. And of course, the huge volume of intricate RPC traffic that handles all the replication and management. If an attacker can get to any of those ports publicly, the domain is compromised almost immediately.
It's game over. And this is what drives our fundamental network design. DCs must reside solely in private subnets. This means private IP addresses only, and the only path they have to the internet has to be strictly outbound, through a mechanism that is designed for controlled egress.
Okay, so let's start laying out that network foundation. And this begins with our dedicated AWS Virtual Private Cloud, our VPC. This is our secure perimeter.
And we need to use clear, distinct CIDR blocks. So let's map out a quick example. Let's say your VPC CIDR is 10.0.0.01 Cs.
Okay.
Inside that, we prioritize resilience right away. We need our DCs in two different availability zones, or AZs. So we'll create two private subnets, 10.1.1.024, let's call it private A, and 10.2.0.024 private B. Our DCs, DC01 and DC02, are going to live in there.
And this immediately brings up the first big architectural question, doesn't it? This is the place where most initial designs just fail. How do we handle internet access? We have two key players here. The Internet Gateway, or IGW, and the NAT Gateway.
And the distinction is so vital. The Internet Gateway, the IGW, is essentially the front door of your VPC. It enables traffic from the public internet to reach resources that have public IPs.
Okay, but hold on a minute. Let me play devil's advocate. If I launch an EC2 instance in a private subnet and I don't assign a public IP address, can I just rely on my security group to block inbound traffic on those ports? Isn't that enough security?
That is the common misconception, and it is absolutely 100% insufficient.
Why?
Because a security group is a stateful packet filtering firewall. The route table, on the other hand, is the fundamental layer 3 rule that dictates where traffic can physically go. So if you route that private subnet to the IGW, you create what we call a ticking time bomb.
A ticking time bomb.
Okay.
Elaborate on that risk. What does that mean?
Yes. So imagine this. A malicious insider, or maybe just an accidental automation script, assigns a public IP address to that DC instance, or maybe they attach an elastic IP.
Right.
That route table entry that's pointing 0.0.000 to the IGW is now active, and in that instant, it makes your domain controller publicly routable on the internet. You should never, ever rely on the absence of a public IP for security. You have to rely on the network routing to make the DC truly invisible.
So the rule has to be, private subnets must never have a route pointing to the IGW, period.
Period.
Understood.
Yeah.
So security has to start at the network layer, not the firewall layer. Okay, so if the DC is truly invisible, how does it get out? I mean, it still needs patches, it needs updates.
And that's where the NAT gateway comes in. The NAT gateway has to live in a public subnet, a subnet that does have a route to the IGW. But the NAT gateway's only function is to provide controlled, outbound-only internet access for all the resources in your private subnets. Think of it like a one-way security checkpoint. Stuff can go out, but nothing can come in.
And this controlled outbound path is vital for just keeping things running, isn't it? We're talking about essential functions like downloading Windows updates, fetching certificates, installing agents like the Systems Manager or SSM agent.
And communicating with vital AWS APIs for management tasks.
Exactly.
The NAT gateway is the secure one-way exit ramp for all of that necessary external chatter.
Okay, so to tie all this together, we need a very precise, mandatory route table blueprint.
Yep.
If you get these three tables right, you've pretty much won half the security battle right there.
All right, let's lay them out. The first one is the public route table. This one's simple. Its mandate is 0.0.0.00 routes to the Internet Gateway, the IGW. And this table is attached only to the public subnet where your NAT gateway lives.
Correct. The second one, and this is the most critical, is the private route table for the DCs. This one has three key lines. Line 1, 0.0.00 routes to the NAT gateway. That gives you your secure internet egress.
Okay.
Line 2 is the hybrid component. It routes your on-premises network, CIDR. Let's use our example. 10.0.016 stinks directly to your VPN attachment or your transit gateway. This keeps all of your AD replication traffic internal and private.
What happens if I forget that second line? If I forget the 10.0.0.016 route?
It's an instant disaster. If the AWS DC tries to talk to the on-prem DC, the routing table will look at it and say, I don't have a specific route for 10.0.0.016, so I'll just send it out through the default route, which is 0.0.000.
To the NAT gateway. To the NAT gateway. And the NAT gateway will then try to send this private IP range traffic out to the public internet, where, of course, it will be immediately dropped. Replication fails before it even starts, all because the packets can't find their way across the secure tunnel.
That distinction is so critical. All right, what's the third route table?
That's the VPN route table. This one ensures the return path is always maintained. So if a packet leaves the AWS DC and travels through the VPN to your on-prem network needs to know exactly how to send that reply packet back. This table routes the AWS VPC CIDR, our 10.0.0.016, back through the VPN or direct connect tunnel attachment.
And if that's misconfigured?
The on-prem DC can see the AWS DC, but the AWS DC can never complete the handshake. It's like shouting into a void.
So it really sounds like we're building security not just by blocking inbound traffic, but by meticulously defining every single permitted path, both for internal traffic and for external.
Exactly. By enforcing this detailed route table structure, your DCs are completely isolated, their internet access is limited to only necessary outbound functions, and that sacred communication channel with your on-prem network is secure and clearly defined. This is the real difference between a network that just works and a highly secure enterprise-grade architecture.
Okay, so we've established the NAT gateway as our secure one-way door to the public internet for things like patching. But here is where we need to refine this blueprint further. As enterprise architects, we can't stop at good enough.
Right.
Relying only on the NAT gateway for all outbound traffic, even traffic that's destined for other AWS services. That feels inherently risky and potentially less secure.
It is. It introduces a lot of unnecessary choke points. For example, if your domain controller needs to perform an operation, let's say log into CloudWatch, that traffic would technically hit the NAT gateway, exit the VPC using a public IP address, and then traverse the public AWS network backbone before it finally reaches the CloudWatch service endpoint.
So if that NAT gateway fails, or if we hit the port limits or the bandwidth limits of that NAT, our essential services just break.
Exactly.
Things like monitoring, management, or key management could suddenly go dark. mean, that's an operational nightmare.
It is. And that is why VPC endpoints are not optional. They are absolutely crucial for a fortified DC blueprint. They completely eliminate the need for traffic to leave the VPC boundary to communicate with core AWS services.
So that gives us two immediate wins, right? First, it dramatically increases resilience because we're reducing that single point of failure that the NAT gateway represents.
And second, it reinforces the private-only model by ensuring that critical service traffic stays entirely within the secure Amazon network perimeter. It never has to traverse the public internet route at all.
So essentially, they're like private network interfaces that you just drop directly into your private subnets, and they let your DCs talk to AWS services over the internal network backbone, completely bypassing the NAT.
That's a perfect way to put it.
So let's detail the required endpoints. These are the absolute essentials for DC operation and security.
Okay, so we prioritize management and zero trust principles first. The SSM endpoint is mandatory. This stands for Systems Manager, and it allows us to use something called Session Manager for remote administration.
This is a huge security benefit that we need to expand on. Why is the SSM endpoint so transformative for DC management compared to the old way of doing things?
Because it completely eliminates the need to open RDP or SSH ports, so port 3389 or 22, anywhere on the DC, even internally.
At all.
At all. Historically, you'd have to manage jump boxes, bastion hosts, really complex security group rules just to allow administrators in. With Session Manager, all that management traffic flows over the internal AWS network, and it's authenticated and audited by IAM. Your DC's management court exposure goes to zero. It just completely changes the compliance conversation.
That is a massive security uplift right there. Okay, what's next on the essential list?
Well, the DC relies heavily on the underlying AWS infrastructure for its own lifecycle and health status. That requires the EC2 endpoint. This is crucial for the AWS agents that are running on the DC to communicate with the EC2 service metadata and the control plane, ensuring proper lifecycle management.
And for operational visibility, we definitely need the CloudWatch Logs endpoint.
Oh, absolutely. DCs are chatterboxes. They generate immense volumes of log data, security logs, application logs, system health events. If we rely on the NAT gateway for shipping all those logs out and the NAT goes down,
you lose all visibility into the environment right when you need it most.
Exactly. The CloudWatch Logs endpoint ensures reliable private transport of all this critical telemetry.
Okay, and finally, security at rest. If we're using encrypted EBS volumes for the DC's operating system and the domain data, we're going to need the key service.
That's the KMS endpoint, Key Management Service. This is required to handle the secured decryption and encryption processes for those encrypted volumes. Without it, the DC might boot, but it literally cannot access its own data securely if it loses connectivity to the KMS service endpoint.
So those four, SSM, EC2, CloudWatch, and KMS, they're the foundation.
Yeah.
But you mentioned there are optional endpoints that can really push the architecture from good to great.
For sure. Consider the S3 gateway endpoint. If you rely on S3 buckets, and a lot of organizations do, for storing patching scripts, automation files, or configuration backups, using a gateway endpoint allows the DCs to pull that data without incurring NAT gateway processing fees.
And more importantly, without introducing another NAT dependency.
Exactly. It's fantastic for high-resilience access to static storage.
And for organizations that are really dedicated to a zero-trust model, we should probably talk about credential management. I mean, hard-coding domain, join credentials into your server, build scripts is dangerous.
It's very dangerous. And that's where the Secrets Manager endpoint comes in. By using Secrets Manager, your automation scripts, like the user data when you launch the instance, can securely retrieve temporary rotational join credentials from Secrets Manager over the private network.
Which keeps sensitive passwords off the server image entirely and ensures they're always managed centrally.
Right. The overall strategic takeaway here is that every single one of these endpoints is a step toward making your domain controllers fully autonomous and hyper-secure. They can operate exclusively within a defined private perimeter, even when they're communicating with core cloud infrastructure.
Okay, we've established the network perimeter and we've secured the egress path. Now we need to define the gates of the fortress, the firewall rules. In AWS, these are the security groups, or SGs.
Security groups are really powerful because they're stateful firewalls. So if we allow a connection in, the return traffic out on that same connection is automatically permitted.
Which simplifies our rules a lot, but we have to be absolutely meticulous about what we let in.
Meticulous is the right word. And it means restricting the source. Since these are domain controllers in a hybrid setup, the only sources of inbound traffic should be from the on-premises AD subnet, our 10.1.0.016 example, and the other AWS DC subnets, so 10.20.0.016. Nothing else should be talking to these ports.
Let's walk through that required inbound rules matrix. These are really the lifeblood ports of Active Directory, and they have to be opened bidirectionally between on-prem and the cloud.
Okay, we'll start with the basics. DNS, that's port 53, both TCP and UDP. This is completely non-negotiable for name resolution and for finding those critical SRV records that point clients to the DCs.
Next, Kerberos port 88, also TCP and UDP. This is the primary authentication ticket exchange mechanism. If this is blocked, nothing logs in.
Simple as that. Directory querying is handled by LDAC and LDAPS, so that's ports 389 for TCP UDP and 636 for TCP. And we strongly recommend enabling LDAPS on 636 to encrypt all that directory query traffic. Plain LDAP exposes sensitive data.
Good tip. Replication requires SMB port 445 TCP. This is needed for accessing the SYS VL and netlogon shares. If this port is blocked, group policy processing breaks instantly.
Right, and for efficient searches across a multi-domain forest, you'll need global catalog. That's ports 3268 and 3269 TCP.
We also need to keep time in check with W32 time on port 123 UDP. And we'll talk more about this later, but time synchronization is absolutely vital for Kerberos.
It is. And finally, a less critical but still necessary administrative port. AD Web Services on port 9389 TCP. This is often used by tools like Server Manager.
Okay, so that covers the static known ports. But now we have to address the single biggest cause of silent replication failure in hybrid Active Directory.
The RPC dynamic port nightmare.
That's the one. This is the part that even senior engineers miss until they're looking at a 2-day replication delay and pulling their hair out.
Oh, I've seen it happen so many times.
So remind us, why is RPC traffic so incredibly difficult to handle in a firewall environment?
Because it uses two steps. The initial communication starts predictably. It uses the RPC endpoint mapper on port 135 TCP. This is like a handshake. The initiating DC says, hey, partner, I want to replicate with you. What ports are you using?
And the receiving DC doesn't just reply with port 135.
No, that is the trap. The receiving DC replies with a random dynamic port over which the actual replication data is going to flow. And by default, the Windows Server OS reserves the entire massive port range from 49142 all the way up to 65535 for this purpose.
That's over 16,000 potential ports.
16,000.
16,000 ports that need to be opened just for Active Directory replication.
Yeah.
I mean, that sounds like a complete security and management nightmare for any firewall, let alone a high-performance one like a security group.
It is a structural nightmare. Imagine trying to manage a security group rule with an entry for TCP 49152.65535, allowing traffic in from your on-prem network. It's way too permissive, it's difficult to audit, and it's just structurally inefficient for a service that really should only need a few hundred dedicated ports.
And if you block this range,
replication fails silently. It often shows up as authentication delays or logon issues hours or even days later. It can look exactly like a DNS problem, because the initial handshake on 135 succeeds, but then the subsequent data transfer just breaks.
So we need the actionable fix, the viral nugget that makes this architecture clean and secure. How do we shrink that massive 16,000 port range down to a manageable size?
We enforce the range via the Windows registry on the domain controller itself. This is a configuration trick that every single hybrid architect has to know. You use PowerShell to create specific registry keys under HKLM software Microsoft RPC Internet.
And what are we telling the operating system to do with this registry change?
You're setting the port's value to a much smaller, dedicated, and auditable range. For instance, we typically specify a custom range like 50,000 to 1,000. This forces the DC to only use those 1,000 ports for all of its dynamic replication and administrative RPC traffic.
And there are a couple other keys too, right?
Yes, you also need to set the port's internet available key to Y and the use internet port's key to Y to make sure it actually follows the new rules.
So now, instead of opening 16,000 ports in our security group, we only have to explicitly open port 135 TCP and that much tighter 50,000 to 1,000 TCP range. I mean, that's a game changer for security and stability.
Let me share a quick anecdote on why this is so important. I was troubleshooting for a client where replication between their new AWS DCs and their on-prem DCs was failing every 3 hours, precisely on the dot.
Every 3 hours.
Like clockwork. DC diag was clean, DNS checked out, but repadmin showed failures. We spent days chasing NAT timeouts, but the issue was simple. Their legacy on-prem firewall had an application layer gateway that kept resetting connections on high ports after 2 hours of inactivity. And because the dynamic port range was so wide, the firewall just couldn't reliably maintain state for that range.
And the fix.
We restricted the range to 1,000 ports, the firewall could handle it cleanly, and the replication failures vanished instantly.
That really highlights why this fix is so vital. It's not just about security, it's about interoperability with legacy firewalls.
Exactly. And we have to stress the mirroring requirement. These exact bidirectional rules, all of them, especially 135 TCP and that custom high port range, they must be mirrored on the on-premises firewall that's handling the VPN or direct connect traffic. A perfect SG in AWS is completely useless if the on-prem router is silently dropping the replication reply packets.
If the networking is the infrastructure, then DNS is really the operating system for Active Directory, isn't it? If DNS breaks, AD is just instantly paralyzed. For hybrid AD to feel seamless, this handshake has to be instantaneous and flawless.
We have to get DNS configuration perfectly right in this scenario. Rule 1 is a safety check. Never, under any circumstances, should you use Amazon-provided DNS, the .2 address in the VPC.
Why not?
That address knows absolutely nothing about your domain. And if an AWS DC tries to use it as a primary or even a secondary server, all domain resolution fails immediately. AWS DCs must use only domain DNS servers.
Okay, so let's detail the specific DNS server configuration blueprint that's required for resilience and speed. We need a kind of cross-referencing structure here.
For the AWS DC01, we're going to set its primary DNS to itself. So, for example, 10.1.1.20. This ensures it can always resolve its own records instantly. Then we set its secondary DNS to the on-premises DC, so 10.1.1.10.
And then for the on-prem DC01, it's the reverse. Its secondary DNS has to be the AWS DC, so 10.20.1.10. This cross-pollination ensures that if the local DC is unavailable for some reason, the remaining DC can immediately reach out across that secure tunnel to the partner environment for resolution.
And this primary-secondary configuration handles basic failover. But for optimal performance and really rapid cross-environment DC location, we have to move beyond simple forwarders to conditional forwarders.
Okay, challenge me on this. If I already have the IPs cross-referenced in my primary-secondary settings, why do I need conditional forwarders? Isn't that just adding complexity?
It's adding efficiency and specific zone control. A simple forwarder takes all external queries that the local DNS can't resolve and just forwards them out. But a conditional forwarder...
It's more targeted?
Precisely. It's laser-focused. A conditional forwarder says, if a query comes in for this specific AD domain, like corp.example.com, I will only forward that query to this specific set of IP addresses.
So on the on-premises DCs, we create a conditional forwarder that says all queries for corp.example.com should be forwarded to the AWS DC IPs, the 10.20.x.x, and on the AWS DCs, the inverse is set up, forwarding queries for the same domain back to the on-prem DC IPs.
And this is so critical for SRV record lookups. When an on-prem client tries to find a domain controller, it queries for SRV records. If the local DC doesn't have the fastest answer, the conditional forwarder ensures that that query doesn't try to go out to the internet or loop infinitely. It sends it directly across the VPN tunnel to the partner DNS server, which is authoritative for the entire domain.
And this seamless resolution ensures clients always authenticate, using the closest site-based DC, maintaining that hybrid functionality without any delay.
But that seamless functionality depends entirely on Part B, flawless routing and replication flow. DNS relies on the physical connectivity being perfect.
Right. Active Directory replication, site link management, even a successful login from a remote client, it's all impossible without true bidirectional routes between your on-prem network and your AWS VPC. Both networks have to know the route to the other's entire CIDR block.
So on the on-prem side, the mandate is crystal clear. Your edge router or your firewall must have a path defined. Send the entire AWS VPC range, so 10.0.0.016, over the VPN or the direct connect link.
And we covered the inverse rule in section 1, but it really bears repeating because you said it's the #1 cause of failure.
It absolutely is. The AWS private route table must have the reciprocal route. Send the entire on-prem range, 10.10.016, back to the VPN attachment or the transit gateway. If that return route is missing, the connection handshake will fail every single time.
And this is why, in larger organizations, the transit gateway, or TGW, becomes the preferred solution. It just abstracts away a lot of these manual routing headaches.
The TGW simplifies the mess. Instead of manually managing route propagation in potentially dozens of VPCs and VPN connections, you centralize it. You attach both the VPC and the VPN to the TGW, and the TGW handles the central routing table. You just tell the TGW, if traffic comes from the VPC, route the 10.0.016 destination to the VPN attachment, and vice versa. The TGW then manages all the dynamic routing updates, which drastically reduces the chance of human configuration error and ensures you have scalable connectivity.
Okay, we have to highlight the really insidious common routing mistakes here because they're often not firewall rules, but these subtle network misconfigurations that are hard to spot.
Beyond just forgetting the return route entry, you have to watch out for the often invisible killer, MTU mismatches.
Maximum transmission unit.
Exactly. If the MTU is incorrectly set on the VPN tunnel, especially for IPsec or Direct Connect, large packets carrying replication data get fragmented and then they get dropped. And this often presents as intermittent replication failure, which is infuriatingly difficult to troubleshoot.
And the firewall issue isn't always just about port blocking, is it?
Correct. You have to watch out for firewall application layer gateways, or ALGs. Some older firewall devices, they try to interpret the sensitive protocols like LDAP or RPC traffic. They might perform ASCII translation or try to inspect the payload, which causes the connection to drop silently because the firewall is literally interfering with the protocol itself.
So if you suspect that, what's the fix?
You disable protocol inspection for the specific 80 ports or, use a modern firewall that understands the traffic without trying to interfere with it.
And finally, always verify the route propagation to your private subnets. You might update the main VPC route table, but if that update doesn't automatically propagate to the specific private subnet attached to a DC, the road is effectively missing. Okay, we've engineered the network, we've established the routing, and we've secured the ports. Now, let's talk about the practical process of actually getting the DCs deployed and ensuring we maintain that enterprise-grade security hardening after promotion.
Deploying a DC in AWS is pretty similar to on-premises, but the sequence and the environment are absolutely crucial, specifically because we're operating over a newly established hybrid link.
On-prem is straightforward, right? You build the server, give it a static IP, join the domain, install ADDS, and promote it. What are the mandatory cloud-aware steps we have to follow here?
First, you launch the Windows Server AMI directly into the designated private subnet, our 10.201.1.024. Second, during the configuration stage, you must confirm that public IP address assignment is explicitly disabled. Non-negotiable. Third, the security group has to be immediately attached and locked down to only those specific 80 ports we detailed back in Section 3.
And the initial DNS configuration has to prioritize the existing environment, right?
Yes. Before you promote it, the new AWS server's primary DNS must point only to the existing on-premises DC. You join the domain over the established VPN or Direct Connect link. This confirms that your networking is actually functional before you commit to the DC promotion.
And only once the server is successfully joined can you then promote it to a domain controller.
Exactly. You'd use the install ADS domain controller command.
Okay, so once it's promoted, the network topology has to be correctly defined using AD sites and subnets. This is so vital for client performance and replication efficiency.
It's often overlooked, and it leads to slow logins and a ton of unnecessary cross-site traffic. You must define the topology. You need to create at least 2 sites in Active Directory sites and services. Site 1 for on-prem and Site 2 for AWS.
And why is this site definition so important? What does it actually do?
Because Active Directory uses the client's source IP address to map them to the closest available DC. So if you don't define the AWS subnets, the 10.20.x.x range, and associate them with the AWS site, clients in the cloud, like your application servers, might end up querying the on-prem DCs first.
Which adds latency to every single authentication request.
Every single one. By associating 10.20.x.x with the AWS site, all of your cloud-hosted applications will prioritize the local, fast AWS DCs for authentication.
So that ensures performance. You then set up the site links and the replication schedules between Site 1 and Site 2.
Correct. The default replication schedule is typically every 15 minutes, but you can adjust this based on the quality of your Direct Connect link. The key is ensuring that intrasite replication, so within the AWS VPC, is fast, and intersite replication across the VPN is reliable.
Let's move to the security hardening checklist. What are the non-negotiable must-haves for maintaining this fortress state?
First, no direct RDP access. Use SSM Session Manager exclusively. Eliminate that port 3D389 exposure entirely.
Second, encryption at rest.
Enable EBS encryption for all volumes using KMS keys. This protects the core directory data even if the underlying instance storage is somehow physically accessed.
Third, strict network segmentation. Review those security group ports one last time. Restrict all of the rules to the exact specific CIDRs only. Absolutely no 0.0.000 allowed, especially for your inbound rules.
Fourth, secure protocols. Enable LDAPS, secure LDAP, and ensure all your directory queries are encrypted. This does require installing a server certificate on the DCs from your internal certificate authority.
And fifth, zero trust credential management. Utilize AWS Secrets Manager to store administrative passwords or serve as account credentials. These secrets should be retrieved at runtime by automation, never hard-coded onto the EC2 instance or stored in plain text.
Okay, let's dedicate a moment to the Kerberos killer. Time synchronization. This is so critical. Kerberos is notoriously sensitive. If a client's clock or a DC's clock is off by more than 5 minutes, authentication requests are instantly rejected. And in a hybrid environment, maintaining synchronization is complex because you have multiple time sources that could potentially be interfering with each other.
So what's the definitive hierarchy? How should it work?
The chain of command has to be enforced. Your entire domain relies on one single source of truth. The on-premises PDC emulator, that's the domain controller that holds the time role.
Okay.
That PDC emulator must be configured to sync from a valid, reliable external NTP source like NIST or pool.ntp.org. Every other DC, including all the AWS DCs, must sync its time only from the PDC emulator.
And that ensures perfect consistency across the entire hybrid domain. Finally, patching. We isolated these DCs using VPC endpoints. We don't want to compromise that isolation just for Windows Update.
This is where SSM Patch Manager really shines. Because we installed the SSM agent and we configured the SSM and EC2 endpoints, we can use Patch Manager to orchestrate and apply patches securely. The DCs will pull the updates from Microsoft via the NAT gateway, but the entire management process is handled internally over the AWS network. This guarantees the DCs never have to talk directly to the public internet for maintenance.
The blueprint is built, the DCs are promoted, and the hardening checklist is complete. Now we move to the final stage, verification. We need actionable commands that definitively prove this entire hybrid pipeline is actually functioning.
This is the Senior Architect's Toolkit. If you run these 4 commands and they all pass, you know your architecture is sound.
Okay, let's start with the essential system check, DCD-IAG-V.
This is the single most important sanity check. It performs a comprehensive test of DNS registration, network connectivity, replication status, service health, basically everything. You were looking for a wall of past results. Any failure here points to a fundamental misconfiguration, usually DNS or routing.
Replication status. We need to know if the data is actually flowing.
For that, you use repadmin REPL summary and repadmin show REPL. The summary gives you a quick health report across all of your replication partners. Show REPL gives you granular details on the last successful synchronization time and any status codes. If you see high failure counts or replication times and days, you have an immediate problem.
DNS validation, the lifeblood check.
In ClickUp-Cotway type SRV, ldap.tcp.dc.msdcs.corp.example.com. This verifies that DNS resolution for DC location via those crucial SRV records is functioning bidirectionally. If this command fails to return the IPs of all your DCs, both on-prem and in AWS, your conditional forwarders are misconfigured or the underlying routing tunnel is broken.
And finally, the time check, catching the Kerberos killer before it strikes.
W32T EMEA query status. This verifies where your DC is getting its time from and ensures it's syncing correctly from the PDC emulator. It checks the time stratum. If the stratum is wrong or the source is the internal CMOS clock rather than the PDC emulator, you have a looming Kerberos outage on your hands.
Okay, let's turn to the top 5 common failures. When something does fail, this is the rapid-fire structured troubleshooting list. What's number 1?
Number 1, the missing route table return path. The AWS DC initiates the connection, but the on-prem DC's reply packet, so 10.9.0.016 back to 10.2.0.0.016, is getting dropped because the return route via the VPN or TGW is missing in the AWS private route table.
What's the signature for that?
You run testnet connection port 389 from AWS to on-prem and it succeeds. You run it from on-prem to AWS and it just stalls. That's the signature.
Number 2.
RPC high port blocked. It's the dynamic range, either 49152.655.35 or your custom 50,000 to 51,000 range that is blocked. This is usually on the on-prem firewall or the AWS security group. The initial connection on 135 succeeds, but the actual data transfer fails.
Number 3.
DNS forwarder misconfigured, conditional forwarders are pointing to the wrong IP, or an AWS DC somehow picked up Amazon-provided DNS as a resolver, SRV lookups fail, and DCAG starts throwing DNS errors.
Number 4.
On-prem firewall blocking critical ports. The on-prem firewall is often older and less cloud-aware than an AWS security group. It might be blocking LDAP on 389 or the entire dynamic RPC range, silently killing replication traffic that's coming through the VPN.
And number 5.
VPN tunnel health, or an MTU mismatch. The entire tunnel might be flapping, or large replication packets are suffering fragmentation because of maximum transmission unit size limits on the VPN tunnel interface. For this, you'll see intermittent connection resets, often tied to scheduled replication times.
So if replication is stalled, what is the rapid-fire troubleshooting flow? Where do you start?
First, check routing and basic port connectivity. Forget about AD for a second. Can you successfully run testnet connection -port 389 from the on-prem DC to the AWS DC and vice versa? If that fails, your problem is strictly layer 3. It's routing, the firewall, or the VPN tunnel itself.
And if that networking check passes, where do you go next?
Second, validate DNS resolution. Use that nslookup SRV command. If that fails, go fix your conditional forwarders. If DNS works, then move to the third step. Validate AD sites and time, make sure the subnets are correctly assigned and that time synchronization is healthy using W32 TSA meters.
So if all those fundamental layers, network, ports, DNS, time are correct, and replication is still stalled, you have to assume AD corruption or some kind of temporary state issue.
That's when you bring out the heavy artillery. Force replication and restart netlogin. You can use repadmin syncl AED to force synchronization across all naming contexts. And if that fails, often just simply restarting the netlogin service on the stalled DC is enough to force it to re-register its network presence and reestablish its replication partnership.
This systematic levered approach ensures you can efficiently pinpoint the failure, moving quickly past the red herrings and straight to the architectural root cause. So what does this all mean?
Well, it means that securely integrating domain controllers into a hybrid cloud environment it's really a masterclass in architectural precision. It requires meticulous attention to detail at every single layer, from the routing tables all the way down to the registry keys.
This is really the difference between an accidental migration and a resilient, secure, enterprise-grade directory service.
It is.
We've given you the end-to-end blueprint today, the correct routing tables and that internet gateway versus NAT gateway distinction, the resilience you get from VPC endpoints, the detailed security group rules you need to keep AD alive.
And most importantly, that specific trick to restrict the RPC high ports for stability and security.
Operational resilience hinges entirely on mastering this complex integration. You really have to treat this blueprint as gospel.
You do. If you skip one layer, especially the routing or the DNS configuration, your entire identity structure just becomes incredibly fragile.
And that leads us to our final provocative thought. If you have perfectly secured your domain controllers using this architecture, enforcing the principle that they must never ever see the public internet, you have essentially raised the bar for attackers. So what is the single next most vulnerable identity service in your architecture that still relies on those same fragile, high-numbered RPC ports?
Think about your certificate authorities, maybe your privileged access management servers, or even your ADFS servers. They all require similar complex port access, and they become the next key target once your DCs are properly locked down.
Something to ponder as you review your internal security posture. Thank you for diving deep with us.
My pleasure.
We'll catch you next time on The Deep Dive.